network geometry view. So now we want to start picking up where looking at the different geometric elements, looking at the links and things like that to make sure that the actual geometry of the network has been set up as we've decided, or as it should be. So the first step is we're going to make sure that we are looking at the boundary conditions of our simulation. Now, there is some guidance in the protocol that we want to look at that determines where the boundaries of your network should be. So in this case, if we look at the I-70 corridor study, right, we're going from this State Road 370 over to Earth City Expressway. If this is going to be our study area, if this dashed red line is our particular study area, then what we want to do is we want to look at what guidelines we have for that. And so at least for freeways, we want to go at least one interchange beyond the construction limits, including the interchanges on ramps and off ramps closest to the construction at minimum, or an evaluation of a full adjacent interchanges, right? So if this is our model limit, typically the guidance will say you want to go, you want to fully contain those boundary interchanges, but you might consider going one interchange beyond. For example, we have a major interchange just to the east of this Earth City Expressway, 270, right? So it might be worth it. It might be better context with the larger simulation to include that. For things like ramp terminals, one major intersection beyond the ramp. Arterials, one major intersection on either end of the project. So there is some guidance, and so that'll be the first thing you want to look at is, do we have the right number of intersections for our study area? The next thing we're going to do is we're going to check the network connectivity. And so again, we can do this simulation check network. What this will do is, beyond just checking for RBC errors, this button will also allow us to check for any breakages in the network. Are we missing a link, or are we missing a connector, or maybe a route has been broken or something like that? So you can always hit that check network. But you'll also want to go in and look at the intersections and make sure all the turning movements are included. We have a graphic overlay for that we're going to be looking at here in a second. Here is just a excerpt from the Vissim protocol. I'm not going to go through every one of these steps, but I've included it in the PowerPoint in case you're using the PowerPoint in the future as part of your review process. But there are some general guidance here as well, pertaining to things like acceleration lanes and grade information. So as we're going through and reviewing the geometry, I wanted to point out some quick things that are common to see within Vissim. The first one I wanted to take a look at was our turning pockets. In Vissim, there are a few different ways that you can model various network elements. So if we talk about turn pockets, there's two primary ways that people model turn pockets. One is as a connector from start to finish. So we can see where the turn pocket starts all the way through the actual turning movement itself is one long connector as a separate entity from the through lanes. The other way that we see it built out is as one the entire approach is considered one link. Both of these are acceptable. It just depends on what you want your simulation to do. For example, the exclusive link option gives you more control over where the queue is forming. So in this case, the queue will form and fill up the entire turn pocket and then spill out into the adjacent lane once the turn pocket is completely full. However, the second option, when you're using multiple lanes on the single connector, this is A, how it's going to import if you're importing from other software platforms. And B, this is going to give you access to that turn pocket at any point along the approach. So if you have a condition where vehicles in the field are regularly making last-minute dives into trying to jump a queue or something like that, you want to replicate that by modeling it like the second option. The next place I want to point out are lane adds and drops. And in this case, there are two ways that you can model lane adds and lane drops. One is kind of the traditional style. It's like a boxy kind of method where basically you're going to look at the striping of the taper itself, which I've indicated here with the yellow line. And what you're going to do is you're going to find where a vehicle can comfortably fit within the new lane or where it can no longer fit within within the terminating lane. And that's where you're going to terminate that extra lane. So you're going to have a 2-lane link and it's dropping down to a 1-lane link, and the through lane is, for example, on the right side, right? So in this case, you're going to look at the taper and you're going to see where can a car comfortably fit within that tapered section and where can it not, and that's going to be where you're going to terminate that extra lane. However, there is a way to model a tapered lane, in which case you can see here we have a 2-lane link, and then it kind of tapers down to, it's still technically a 2-lane link, but you can see that there's like a little bit of a chunk at the end of there. And what we're doing is we're just basically taking what would otherwise be a rectangle, and we made one edge of that rectangle about a half a foot wide, and so it tapers down. This takes a couple more steps to create this tapered option, but if you have a very long gradual taper, for example, on a freeway or something like that, this taper method is going to give you more zipper-like behavior in terms of the merging and weaving. Whereas the box method is going to be more akin to really short sudden tapers, for example, on arterials, where you have a turn pocket starting or a target lane, an exit lane pocket that is ending. Something like that, you're gonna probably see these these boxing methods used a little bit more. Whereas if you have a long gradual taper where vehicles are kind of merging together at high speeds, or they're trying to zipper like on an on-ramp, this tapered method can actually replicate that behavior a little bit better. Not that the box method is wrong in those conditions, it's just it takes a little bit more calibration on the driver behavior side to get that zippering behavior to work if you're using the box method. But both of these are correct, but these are what you're going to be looking for. Um, The next one I'm going to point out are multi-lane roundabouts or multi-lane movements. Sometimes people like to model these as independent links. That's totally fine, but it is also okay to see these modeled as 2-lane links until the actual diverge point. So you'll see both models being executed there. And we're going to be jumping back into Vissim after I kind of describe all of these sections. We're also going to be looking at the lane change parameters, and in Vissim, how that's indicated is if you see the dashed lines, that's just a free lane change, so people can go in any direction. If you see one side of the lane divider being solid, that's preventing a lane change in that direction, out of that lane. So in this case, if the lane divider is on the right, is solid, that means that nobody can cross that from right to left. If it's on the left side, nobody can cross it from left to right. And if it's just one solid line, then there's no lane changes at all. So those are going to be indicated on the network editor, and that'll be a way to spot check that. A lot of times you're going to see these no lane change left or rights at the start or end um, of particular sections of the freeway. For example, maybe you have an HOV lane and there's an exit coming up. So you might have this no lane change left because people want to be able to exit the HOV lane, but you don't want new people going into the HOV lane, right? Or maybe you have a turn pocket or something like that that you don't want people diving in and out of all the time. The last bit that we're going to look at here real quick is that you want to make sure that your network is scaled correctly. Now, the Bing Maps aerials are always scaled correctly. But if somebody's using like a background image or something like that, sometimes it's not uncommon to have those background images accidentally be scaled too big or too small, in which case your links are going to be too long or too short, and that will affect things like travel times and gap acceptances. So you'll want to make sure that your network scale is appropriate. And again, we're going to go through all this again. I'm just kind of laying it out for you ahead of time. Um, uh, and then we're going to go back through and we're going to do all this in the network. A big step of this is that you're going to be making sure that the lane geometry matches up with the aerial imagery or any sort of background images that you might have. So this is going to be mostly just kind of spot checking the network and making sure that the intersections seem laid out okay. Um, with the appropriate number of lanes and things like that. It's not always going to be exactly perfect. It might look a little jagged with the spline points, or the lane divider might be off by an inch or two or something like that. That's okay. It doesn't necessarily need to be exactly perfectly perfect, but you want to make sure all the elements are there. Does it have a turn pocket? Does it have the correct length of turn bays? Um, is the spline of the link generally following the spline of the roadway underneath? So now we're going to jump in and we're going to give it a try within Vissim. So let me jump into my Vissim network. So where we left off on our checklist up in the corner was we checked our seating period. But now what we want to do is we want to go to step 6 and we're going to check our network boundaries. So just giving it a look, here we can see that we've changed the background image to be an OpenStreetMaps background image so we can actually see the street names. And again, we're looking at a model that's going from this State Road 370 all the way down to this Earth City um, expressway here. And so if we kind of zoom in, we can see that they've extended the freeway through this interchange. They haven't included the I-270 interchange. Sometimes if you see this, you'll see an on-ramp or something like that. So that'll be something that you want to look out for to make sure that, if this weave is really short. For example, if I measure the length of where this merge point is to where this diverge point is, we're less than a mile apart. So that might be cause for concern if it gets too congested. If this on ramp is regularly congested, it might be beneficial to the simulation to include that on ramp to see if that weaving at this input location limits the throughput of this eastbound movement at all. The other place we're going to check is on the arterials. So if you remember the guidance, the Vissim protocol says, if you're doing off ramp, you want to extend at least one intersection, and we definitely have at least one intersection in either direction. And if we're doing an arterial, if we're doing a proper arterial study on some of these, you'd want to make sure that it extends at least one intersection beyond the bounds of that arterial study. But this is more focusing on kind of a freeway. So the big thing we're looking at are nearby interchanges of making sure that we have enough space for merging and weaving behaviors to happen. After we've checked the network boundaries and we've determined that those are okay, we're going to check network connectivity. So we're going to go through and we're going to double check again using simulation check network. And in this case, we didn't get any warnings down in the corner. There are no warnings or errors. So at least all of our routes are connected. There's no breaks in the network anywhere. And now what we're going to do is we're just going to double check our network connectivity. And you can kind of mix this step and the check link geometry kind of in the same vein, because you're kind of doing the same thing in both, right? In this case, what we've done is we've colored the links. This graphic overlay colors the links as gray with like a blue outline. And then anytime there is a diverge point or a merge point or a turning movement, those are indicated with these pinkish purple colored connectors. And so you can kind of see any time where there's a lane add or a lane drop, you can see that it's indicated in purple here. You can see the turning movements. And so what you're doing is you're just making sure that all of these movements are appropriately accounted for, right? You're going to look at an intersection and make sure you have your 4 right turn movements in this case, you have your left turn movements, you have your through movements. You're going to see on the ramps, right? So here we have this outbound link and a lane drop, and then we have this inbound link and a lane add here, and then a turn pocket starting right there. So we're just kind of looking and making sure that our network connectivity um, makes sense and that you're not missing any turning movements, um, because that could cause problems down the road if you're missing a turning movement. Say you're missing a left turn or something like that. You also want to make sure that you don't have any links going the inappropriate directions and things like that. So you're just going to move around and spot check the network there. If you click this red box at the top, that'll zoom out and show the entire network again. So after you've checked your network connectivity, next you're going to want to check your network scale. Now, how we can do this is, again, typically the Bing maps, you're not going to have to worry about the scale. But here, for example, we had some background images. What you can do is you can find two known points on your network, and you can measure their distances. So for example, if you know the merge point here and the diverge point here on this particular stretch of the freeway, maybe you have a site plan or something like that that indicates that exact distance. What you can do is you can click a ruler up at the top, and you can measure the distance from here to here and indicate, okay, this is 1,851 feet, right? And you can compare that to what your site plan is or something like that. So that's a good way to double check that your scale is correct. Another way that I do it for the background images is if I know the distance between two known points, like maybe you've gone onto Google Earth or something like that, and you've measured between 2 points. And so you know from Google Earth that the length of this building right here, right? And so you can measure from corner to corner on this background image and make sure that it is scaled correctly. This is something that I've come across before in support through my role as on the support portal. Is I had a user submit a project where all their travel times were about 15% too short, and it took a while, but we eventually figured out that the background images that they had imported, they had scaled inappropriately. And so by tracing over those background images with the links, all of their links were about 15% shorter than they should have been. So all their travel times were much high or much lower than they thought they should be. And unfortunately, there's not a great way to fix that. We don't have a way to just select a bunch of links and scale them up. You have to kind of manually stretch out all those links and kind of redraw them. And so that's a real big indicator if you've made a mistake there. All right. So now that we've checked to make sure our network scale is correct, again, you'll come back and you'll check to make sure that the link geometry is correct. Now here we can zoom in. This is a very similar to checking connectivity, but what we've done is we've made the graphics a little bit see-through. So if you zoom in far enough, you can actually see the lane dividers and making sure that you have the appropriate lanes. Now here we can see that the lanes are a little bit offset, but that's okay if they're a little bit offset laterally. It's not really going to affect your simulation very much, and especially if we look at the start point of the lane and at the end point of the lane, those are kind of lined up correctly. So this turning movement, um, at least this turning movement right here, is in the correct location. Now, as far as laterally being offset, the big thing you're looking for is making sure that these distances aren't negatively affected by it. If it's too far offset, then your distance of your link is going to be bigger, which means that you're going to artificially inflate your storage or your travel times, and you're going to want to avoid that. But it looks like there's a whole section here where some of these links maybe got shifted or something like that. But these ones seem to be pretty online. So there's just a couple. This arterial looks like it was shifted maybe accidentally, or maybe they used a background image or something like that. But you're going to want to make sure that the appropriate number of lanes are being used and the gore points are in the appropriate location and things like that. Here we can also see that we have a no lane change to the right indicator right here. So we can see that we have dashed line, and then we have a solid and a dash line. So that's preventing vehicles from making a lane change to the right, and that's because this lane is ending. And so what the modeler did not want vehicles to do is use this as a passing lane right before it ends. And that's a perfectly acceptable way to model a lane drop, especially a longer lane drop like this, where there might be signs indicating, hey, the lane is ending up ahead, so vehicles would be more likely to stay in the through lanes. Okay. So again, you're going to go through and you're going to check your scope. The actual process of checking the links can be kind of longer. It just depends on how complex the network is. Um, Generally, though, as you're going through and double checking the geometry, the modeler is going to use more or less the same process, at least in my experience. The modelers are going to use more or less the same process for building most of their intersections. So unless there was a whole team of modelers building different sections of the model at a particular time, generally you're going to get to know this modeler's style pretty quickly, and you're going to be able to spot check, and you're going to get to feel if something's out of place, because it's going to be all of a sudden a big jump or a big change in how they decided to model a lane drop or model a particular intersection. Um, and so you'll eventually, as you go through the first couple intersections, it'll take a while, and then you'll kind of speed up in terms of your review process, because you're going to be able to pick up on those little nuances much more quickly, and what that modeler style was. Okay. All right, so the next step in the model review process is to make sure that the link types have been assigned correctly. So we looked at the geometry of the links. The next thing we want to look at are the actual link types. And in this case, we're going to be, what we mean by link types is, I like to think of these as like facility types, right? So you're going to have arterials, you're going to have freeways, you're going to have merging and weaving sections, you're going to have roundabouts, things like that. And each link type is going to have a behavior associated with it. We're going to talk about driver behaviors tomorrow in greater detail. But for this initial step, what we're going to do is we're just going to make sure that different link types are assigned to different links and lanes appropriately. So there's going to be a list of link types that we're going to take a look at in our base data menu. But we also have a graphic overlay. And so I want to describe what the defaults look like, and then our graphic overlay, and then what the example link types are in our model. So here on the left side, we have our default link types. These are the ones that come in when you first open up Vissim for the first time, or when you start a new project. You're going to have these 5 default link types. So again, think of these as facility types, right? And they're kind of broad strokes facility types. So urban is going to be any arterial. Right side rule is going to be kind of like your rural 1-lane highway. Free lane selection, that's going to be obviously your freeways, where basically there's no limiting factors on which lanes they can choose. And then we have footpaths and cycle tracks for crosswalks and bike lanes respectively. And so what we've done is we've created a color scheme that will indicate when a link is one of those default link types. Now, it is common for users to import uh, other networks into Vissim to help start the process. Maybe you have some sort of intersection capacity analysis that you've done in Vistro, or you've done like a travel demand model of some kind, and you've imported that. Those will typically import with a 1000 and then using one of these 5 defaults. So in that case, we've created similar colors, kind of more pastel colors for the imports. And we can actually see that in our example file, there was an imported urban and an imported freeway, probably from some other piece of software. We also have a user-defined link behavior type here, and we can tell based on the numbering scheme that it was user-defined. We also see it has a different name. So here with the default it says urban motorized. With the import it says urban motorized. This one says freeway 1.5 with aggressive. So that's usually an indicator that it was custom created, and that'll come through in the calibration report as well. But any custom defined link behavior types will come in as purple. So you'll be able to quickly spot those out. So we'll be looking at the facility types. Then we'll also be looking at if there are any lanes specifically that are blocked to certain vehicles, right? So maybe you have a bike lane that is blocked to cars, or maybe you have an HOV lane that is blocked to trucks or something like that. Or maybe you have a transit, bus rapid transit that's blocked to everything except for buses or something like that. So you're going to be looking for those types of lane turns as well. The last little bit that we're going to look at here is also going to be our grade summary. So in terms of how Vissim operates, you can add grades to the links, grade percentages to the links, and if you do so, each vehicle has a default acceleration profile and deceleration profile. And for larger vehicles like semi-trucks, that's also adaptive based on the power and weight ratios of the different types of models that are in the simulation. And the grades shift those acceleration profiles up or down depending on if it's an upgrade or a downgrade. And so you can enter grade information onto your links. In that case, it will affect the acceleration and deceleration, so the braking distances or the startup timing if you have a steep ramp or something like that with the signal at the top. And so grade characteristics do have a big impact on the calibration of the model. And so what we have here is a color scheme that will indicate when the grade is within these certain boundaries. So let's take a look at our Vissim model for those next network elements. So again, we left off checking our link geometry, step 9. And so now we're going to jump in and we're going to check our link types. And again, link types are just facility types. So here we have our color scheme. On the right side, we can see that we have our 5 defaults. We have some user added ones, and then we have our imported ones as well. So generally looking around, we see a lot of this pastel red kind of color on the freeway. And if I zoom in, you can see it a little bit better here. So this is indicating that these have been using the imported freeway option. And then you see this pastel yellow color. So it looks like these are using the urban imported color. Now, beyond just checking and making sure what links are assigned, I like to go up into the base data menu and actually open up the link behavior types list. What this will do is this will just show us if they've created any custom ones that maybe they're not using or something like that. Or maybe there might be some links where a specific lane is using one or the other. So if we click on this link behavior types list option, this will open up a list of all of the facility types that are in the network. In this case, we have 3 facility types. We have urban, freeway, and then this freeway 1.5 with aggressive driver behavior. I'm not really sure what that means, but we'll check on that a little bit later. What I'm more curious about right now is if they have this, they probably used it somewhere. And looking around, I don't see it readily available on any of the links. So instead of just spot checking it, what I'm going to do is I'm going to open up my links list. So if I come over to my links layer, I can right click on it and I can say show list. And what that'll do is that will open up a list similar to our link behavior types, but it'll open up a list of all of the links in the network. And so I can show my list. And in our network, we have 1,205 different links throughout the network. Now that's a lot to manually go through and check. So for example, I can zoom in and I can double click on a link and I can check and see if it has a specific link behavior type, maybe assigned to the lane or something like that. But I can do that much more quickly in my links list. So here we have a list of all 1,200 links. And then if you look up at the top, we use this drop down menu. It says lanes. So when I click on a particular link, it shows all of the lanes on that link and what link behavior type is assigned to it. So a quick way to see if there are any lane specific driver behaviors is to just where it says count, if I click this, it will highlight all of the links in the network. If I zoom out, you can see all of the links in the network have been highlighted. And what I could do is on this right side, this shows all of the lanes. So now out of 1,205 links that are in the network, we have 2,223 different lanes in the network as well. So now I can just use this and I can scroll down and quickly look, and I'm looking in this column for link behavior types to see if there are any custom link behavior types used anywhere. And I don't see anything on first glance, but a way to double check that is if I hover over where it says link behavior type, you see this little black filter button come up. So I put my cursor over it, I can click this, and I can look specifically for any lanes that contain this freeway aggressive driver behavior. So if I click this, I'll say I want it to equal, so I'll turn on this checkbox, and I can pick out a specific driver behavior. And in this case, there are no lanes with this specific driver behavior. I can do the same thing on this side. So here's my link list. I can look and I can say, okay, link behavior type. I want to find any link with this driver behavior. But in this particular model, it doesn't look like they've actually used that driver behavior anywhere. Maybe what they did was they created a different model and then copied it over, and this was just an artifact of that copy. Or maybe this was a driver behavior that they're planning on using in a future calibration or a future build model or something like that, and they wanted to include it. That'll be something where we need to check our calibration worksheet. So here there's calibration memo. It might be somewhere in that calibration memo that we can take a look at in the future. But for now, I feel pretty confident that they haven't used it. So they're only using this urban imported and that freeway imported driver behaviors, which tells me that it's probably more or less using default driver behaviors unless they've changed, calibrated those driver behaviors specifically. So I've done a pretty thorough job checking the link types. Now we're going to look at checking lane closures and restrictions. Now this graphic overlay, if I zoom in, what it's doing is it's displaying any lanes that have any blocked vehicle classes. So if I zoom in on the freeway, we can see that any lanes that don't have restrictions are just gray. And if I zoom in far enough, we can see that our freeway links have an orange lane. Oop, don't do that. They have an orange lane indicating that the left lane is blocked to trucks. Now again, I could double click on a link and get more information about it. And I can see, okay, here blocked vehicles. If I use this drop down, we can see that trucks are blocked from the left lane. Similarly to the link behavior types though, I could do the same thing in the list. So I can highlight all of my links and I can filter and I can say, okay, I want to find all of the ones that maybe contain any one of these three, right? And so here we see a bunch of lanes that are all blocked to trucks, and I can highlight these particular lanes. So if I click here, we have 72 different lanes that are blocked to trucks, and they all seem to be along the freeway. So we can see that they all seem to be along the freeway there. So that's a quick way to spot check without having to go to every single link, is to just use the list option and identify, okay, which lanes are blocked to certain vehicle classes, and go from there. Common ones are going to be obviously on your freeway. The left lane is going to be blocked to trucks, or maybe there's an HOV lane, or hard shoulder running with bus rapid transit, or maybe you have a bike lane or something like that. Okay. After we've checked our link closure and restrictions, any special lane characteristics. So in this case, you're looking for anything else that might be weird about your lanes or custom about your lanes. In this case, we're also looking at gradients. So in this case, all of our grades are somewhere between plus or minus 2%, which isn't really going to have too much of an impact on your simulation. So just looking around, it doesn't look like gradient percentages were indicated very much. We could look at gradients in the link list. You'll see that it doesn't have gradient readily available. But if you want to find the gradient, you can always, in the link list, click this attribute selection button. There's a little black wrench right here. And this will allow us to customize what columns we can see. So for example, we don't really care about the display type or the level or the from and to link and stuff like that. So I'm going to click this attribute selection. And this list on the right here, these rows are the same as all of our column headers that we see in our link list. So I can pick out which column headers I want to look at. For example, I don't really care if it's a connector or if it's from a link or to a link. Or has an overtaking lane or any user-defined attribute 1. I don't really care about any of that. But what I do care about in this case is the gradient. So on the right, I'm going to just search for my gradient, and I can just double click on it, or you can use these green arrows, and I can just select this green arrow for gradient. So again, to do that, I click this black wrench in the list. I get rid of any attributes I don't want by clicking this green arrow. Level, display type. And then I can find any attributes I do want. In this case, gradient. I'm going to highlight it and click this green arrow. And I can move it around and reposition it. And so once it's on this side, I can click OK. And now we can look for any links that have a non-zero gradient, right? And so I could use my filter option, and I say, maybe does equals not 0%. And so now I can see that all the links have 0 gradient. If they did have a gradient, it would show up as a color on our background image. But that was just me double checking that I didn't make a mistake with my graphic overlay. So again, up to this point, what we've done is we've checked for any major errors. We've checked to make sure that our simulation period is in the right boundaries. We've checked that our physical network is within the correct boundaries. We've checked for network connectivity. We checked for scale. We've checked that our links are lining up with how we expect them to be in the physical network. We've checked the different facility types, and we've checked for any sort of lane closures and restrictions or any special lane characteristics that we might have missed.